All right, here we go. Hopefully these first, well, at least the first one wasn't too challenging. Get these out of the way. We're verifying, right? So when you're verifying this stuff, you're not quote unquote solving. You're not trying to balance the equation, so to speak. You're trying to take one side and do some substitution, some simplifying, some basic, I can't say algebra, but use some properties of algebra to make this look like this. Right? And there are different approaches to take. Generally speaking, you want to go to the side that looks more complicated and simplify it. It's easier, I know it goes against the logic of teenagers, but you go to the place that looks harder and you do all of the work to make it simpler. Don't go to the side that's simple and try to make it complicated, right? So go to the side where it's like, oh, that looks horrible. I guess I must have to start with that and simplify it. Now this, like we said, not a horrible looking thing to start off with. But from here we have secant, we have sine, we have tangent, right? Technically speaking, there should be a question mark here, because I'm not sure that this is the same as that. I have to prove it. So when you look at this and you say, I'll divide by sine on both sides, because that might, no, you can't. You cannot solve this equation by dividing both sides by something, multiplying, adding, subtracting. You can't do it, all right? What we can do is, since we have three different trig terms, we can substitute sines and cosines in for everything so that it's only two different trig terms. Everything can be written in terms of a sine or a cosine. So in other words, this secant is 1 over cosine. Sine is sine, right? But because this is a fraction, maybe just because it might be easier to look at, maybe we should change our sine theta to sine theta over 1. Just a suggestion, take it or leave it, you don't have to. But if you have one fraction, take the thing that's not a fraction and make it one, so that we're all on the same level, so to speak, right? And tangent is sine over cosine. So my job is to prove, in fact, that this is the same as this. And if we multiply straight across as we do when we're multiplying fractions, we get sine theta over cosine theta, and that is in fact equal to sine theta over cosine theta. Check. Done. Okay. So this is an instance where writing everything in terms of sine and cosine makes sense. All right, let's continue with a different example. Shift these further down the line. Do some more, do some more teenage type things like pushing your problems off to later, right? I speak badly about teenagers, but it's just to like get a smirk because you're like, yeah, you know what, that's actually true, right? You know what I'm saying? All right. Like when we talk about work. Like we won't talk about it here, but when we talk about work with vectors, I like put the word work up on the board and I'm like, oh God, did you guys see that? Like these teenagers are like afraid of work. You can smile. It's true. Okay, here we go. All right, let's take a look at this one. So, like I said, when you take a look at this, you got to recognize certain parts, certain things that just go together sometimes. Okay, you're like, oh well, yeah, I've seen that before. Like cosine squared and sine squared. Everything's already written in terms of cosine squared and sine squared, or cosines and sines, but I have to make this side look like this side, or make this side look like this side. So sometimes you've got to take a step back and say, well, on the left, I see cosine squared. On the right, I don't see that. So how am I going to make this side that has a cosine squared look like that? Well, I know that cosine squared is somehow related to sine squared. There is a relationship that exists there. And if there's a relationship that exists between cosine squared and sine squared, maybe I can substitute sine in. And that's what we want. We want sine squareds on the left because we have them on the right. But I don't have any cosines over here, so I gotta get rid of this. And when I say get rid of, we can't get rid of by subtraction or division. When we get rid of something in these proofs, it's through substitution. We take it out, we put something else more useful in its place. Right? Now we've done this a few times, but we'll do it again. Cosine squared theta, if this is our identity, I'll write it and then I'm going to erase it. This is our margin work. That's our identity. What can I do with cosine squared theta to get it, to write it in terms of sine theta? I can subtract this from both sides. So I know that cosine squared theta is equal to 1 minus sine squared theta. So I get rid of cosine squared by substituting this in its place. And again, it all stems from, I'm going to say this again, I keep coming back to some of the same points, but it comes from the idea that if there's a cosine squared over here and I have to make this look like this, I'm not allowed to have cosine anymore because there's no cosines over here. So we get rid of it. We get rid of it, we say it's equal to 1 minus sine squared minus sine squared, and this is equal to our right side. So I have this quantity, and I am subtracting this from it. So this isn't a distribution that I'm going to do. This is not being multiplied. This is being subtracted. So I don't really need these parentheses, so I'm going to rewrite it without them. And remember that we treat this sine squared as our variable. Theta is technically the variable in this problem. We're not even solving for it, so it doesn't matter. But we treat that trig term as the variable. Meaning what? Meaning I have two of them here. So when I combine two negative sine squared thetas, I have negative 2 sine squared theta, which is what I have over here. Check. Cut. Can make